will first talk a little bit about the Cornerstone activity and what we can offer to the community. And then I'll talk a little bit about the research, in the background that we do as well, and some of the components and potentially systems that we are developing, and you can also develop on the Cornerstone platform. So next slide, please. So in Cornerstone, we offer a range of MPWs, as you perhaps know. And the technology platform varies between standard SOI with different thicknesses to silicon nitride, which offers like 2 different thicknesses these days, because we also look at visible potential systems. And we also have like some germanium on silicon, which really focus more on the mid-infrared activities. And as part of other development, I would say, we also have like some integration capabilities where we can do flip chips and light sources on your chips, some PDs or electronics that we can also bond, and we also offer different services in terms of lithography and e-beam, depending on your requirements, if you have some dedicated needs. So that being said, we have like a range of MPWs that are coming up. In silicon on insulator, 220 is the passive and the active. The active, I'll show you an example of what we did in neuromorphic a couple of years ago, which was quite successful, and that's standard PN junction modulators type of system. When we also have like some silicon nitride coming up, and we have something called the student batch where you get that single edge and reduce cost. One key point of Cornerstone, we have this open platform type of environment where it's an open source PDK, so you can have access to all the designs and all the components, and you can actually use all the ecosystem that is available to you in order to actually develop this further. And there's no attachment to this in terms of IP, so it's free to use. Next slide. All right. So we also do something called a peak bootcamp. So that's quite interesting if you are quite new to the photonic environment and you want to know a bit more about how things are fabricated and how they are designed. So we run a bootcamp next year at a number of occasions that you can see here. If you're interested, just click on the link. But essentially, you come here and you have like interaction with different ways of designing these chips and how we actually do the fabrication and the measurements. So this is quite an interesting training that we do, and we run quite regularly actually. So feel free to click on that. Now I wanted to use my second hat and to show a little bit of the research and what we use Cornerstone for and what we do beyond Cornerstone, because we also do our own activity beyond Cornerstone. Next slide, please. So as you know, computing is really power hungry, and we're talking about nuclear power station to run data centers these days, and literally trillions of dollars to actually feed the infrastructure or even develop it. So this is exponentially increasing. So we need to do something, and this is why we're talking about these things in photonics, I suppose, and all sorts of other activities in neuromorphics as well. So next slide, please. And the point of all of this is really to find ways to get this, to see what silicon photonics can do. And there are 2 ways to look at this, right? There is like the data transfer, which is, sending data at the highest bandwidth possible for the lowest amount of energy. And there is also like trying to achieve computation using photonics, right? So I'll just touch a little bit of both topics today. So next slide, please. So one of the key points in photonics compared to electronics, so just to try to take a step back, electronics, the problem with electronics is that you have extremely high density of devices, and you can do a very, very fast computation in parallel using GPUs, but the memory is not where the computation occurs. So you need to have data transfer between your memory and your compute constantly, right? So that costs power, that costs latency. And it's a bit of a bottleneck that photonics doesn't really have, and any analog circuit, I suppose, doesn't really suffer this kind of a problem. Because the point of photonics is you can pretty much compute at the speed of light. So your light propagates into a system, and you see like different weights or that impact the phase or absorb the light along the way, and you can actually do computation using the devices that I'm showing here. So you can do that in free space using Mach-Zehnders on a chip that gives you that this weight matrix multiplication. You can do that in a non-coherent environment with different sources and ring resonators, and so on and so forth, right? So the idea is always the same. You propagate your light, you have the memory as you propagate, and you try to do computation as you go along. Next slide, please. So here is an example of what we did with some of the Cornerstone active runs. So this is SOI 220 active, for instance. And the point of this was just to demonstrate that using a coherent system and PN junction modulators, we could achieve like literally a rate that was way in excess of what, for instance, NVIDIA could produce, right? With quite a good accuracy as well. So one of the problems with analog type of computation is noise, and that affects your accuracy. And how do you deal with that? This is a complex problem that needs to be addressed. And I think we had a bit of a successful system here where we cascaded like different type of Mach-Zehnders and we try to achieve this coherent photonic neural network. If you're interested in knowing more, you have like the link, and I think the slide will be shared, so you can have a look at this. And this was fabricated with the further active runs in Cornerstone. Next slide, please. So one of the key points that I wanted to make here is, photonics is all about trying to catch up with density of integration, I suppose, that you have in electronics, and it's quite sparse compared to what you have in electronics. So how do you actually achieve that? So you have a plot here demonstrating that you can really increase this density of integration, I suppose, recently. And the other problem is loss on the chip, so you lose a lot of the light as you stack up your devices. So you need amplifiers on chip eventually, right? So these days you have like MTP bonding, you have die bonding, and what I wanted to introduce here is one step further, monolithic integration of stratified on silicon. So instead of bonding stuff and playing Lego a little bit, I would say you grow things in line, so you don't have to actually rely on any other fab, and that would become part of a process line basically. So next slide, please. So this is just like an introduction slide that I think John Bowers came up with that little ladder step. But essentially, you want to have like your laser grown on silicon, and you want to be able to couple that efficiently to a waveguide, right? And so far, you have mixed results on this. And one of the big problems is not actually to grow the laser on silicon, is to couple it to a waveguide efficiently and at wafer scale. Next slide, please. So we came up with a bit of a process that we can scale up to 200 millimeters and potentially 300. And we tried it with something called the quantum confined Stark effect modulator in the O-band. So that's, kind of fitted for like data centers. And the problem with those devices, they're quite sick, right? A micron plus. So how do you actually interface that to a waveguide system that is compatible with, CMOS type of system? So silicon or silicon nitride. And this is exactly what we've done here. So you have this thick, stack that you see in the middle, and you try to couple that to a silicon nitride waveguide, and you can see a cross section, at the bottom right. So you transfer the light from one to the other, and that works with silicon germanium. So next slide, please. And that gives you extremely efficient modulation, 50 odd micron long, and in the O-band. So that's quite difficult to achieve with electron absorption modulators in silicon, because you need a quantum confined Stark effect. So it's one quantum wells, and you need to match lattice and everything and reduce defects, right? But this is actually possible, and we demonstrated it, and that was done at wafer scale, and we got 100G out of this. So it's showing that we can actually achieve that. And we can transfer the light from high index to low index with about 1.5 dB insertion loss and low reflection. So next slide, please. So the obvious next task is, okay, so if you can do that with silicon germanium, you can do that potentially with 3-5 materials, and this is exactly what we did. So you can see that 3-5 materials, if you're on a laser on an amplifier on chip, is 3 or 4 microns thick, right? So you have to work with that. And how do you do it? Well, you use silicon nitride in the same way, and you try to adapt the mode and things like that, right? So next slide, please. And this is what we fabricated. So you have a device, electrically connected in the middle here, and you have your waveguide and nitride waveguide on both sides. So this is what it looks like, and this is a cross section of the device. Next slide, please. And we got, CW, operation out of this, coupled directly to a waveguide. So, we got a few milliwatts, but we have like a couple of, iteration, on the roadmap that will improve that, dramatically down the line. And the next step is also to move that to a more stable 200 millimeter platform. So next slide, please. That's the CW laser in the O-band. And we also have like amplification here, which is the important part, I believe, in any systems. If you have switching or any complex system where you have like a lot of cascaded devices, you need something that enables to amplify your light as you go along. So lossless switches, and so on and so forth, right? So again, here is just like an early demonstrators. We aim for like more than 10 dB, amplification in the O-band, but this is a first demonstration here. Next slide, please. So what's next? Well, as I said, for us is really to drive like density of integration, but density of integration comes with you need a native light source, you need an amplifier. So how do you actually achieve that? And this was just like some examples of what we are planning. And down the line is how do you actually reduce the size of those big lasers, I would say, because they're 2 or 3 millimeter long. What do you do to drive integration further? And try to target that VLSI type of system. Next slide, and that's my acknowledgement, and I will stop there. Thank you.